bottom, I think the only one left is kilogram meters squared per second, no square. You might say, is that a unit for something? Yes. We'll talk about it later. It's called angular momentum, L vector. We see that there's some vectors, there's some scalars, and there's all sorts of combinations of these things. So it's a good thing that we at least have abbreviations for some of them, okay? All right, so what is momentum for? What is it good for? Newton's second law, you may be surprised to learn that the most general form of Newton's second law can be expressed with momentum. So when you apply a net force to an object, what you're actually doing is you're changing its momentum. Here, it's the net force will change the momentum with time. This is the most general form of Newton's second law, and you need momentum to talk about it. So where do we get off using F net equals ma? Let's take a look. Well, momentum, if that's mv, this is the first time we've had two things inside a delta, so we should probably look at what that means. Delta mv means m final v final minus m initial v initial. But I should point out that m is usually not negotiable, so m can be factored out, leaving a delta v. So this is an important factor, or important thing to know about delta math, is that if you have something inside the delta that isn't delta-ing, you can take it out of the delta. Okay? So equals m delta v over delta t. That's if the mass is constant. And here we get our good old familiar F net equals ma. So F net equals ma is actually a special case of the law that assumes that the mass of the object is constant, which, you know, it will be for us, but there are systems that it's not. An example is a rocket ship. Rocket ship's made mostly out of fuel, and you burn that fuel. So the mass that is carried by the rocket gets less and less and less. So not that we'll be doing anything with it, but I do want to emphasize for you that momentum is very important, right? If you want to describe Newton's second law with it, that will give you the ability to describe it in the most general fashion, okay? So, even though this is not very computationally handy, we just end up with F net equals ma for our circumstances, it is useful to look at it a little bit. Let's invert it to get this equation. So this says that if you want to change an object's momentum, you're going to have to apply a net force on it for some period of time. Here's where I point out it makes sense that an alternative unit is Newton seconds, because you're applying a force for some time. The change in momentum is sometimes even called another name. It's called impulse. It's sometimes I vector or sometimes J vector. I'm not going to use either because I'm just going to call it change in momentum. But if you ever come across someone saying impulse, I want you to know what it means. It's just another word for change in momentum. An example, impulse shopping, right? You have your momentum. You're just going to buy your bread and your milk and, ooh, gossip magazines, right? So you change your velocity, and so your momentum has changed as well. Okay? I like to call this one the egg toss equation, because if you know the game of the egg toss, right? You throw egg back and forth, try not to break it. That can help you in your strategizing. If you look at the professional egg tossers, you can see what they do is they catch it very early, as early as they can and then take as long of a time as possible to stop it. And the reason why, you don't have any choice about the change in momentum. The egg gets to you at a certain velocity and you have to bring it to a stop, and the egg has a certain mass, so there's nothing you can do about that left-hand side. But you can choose to take a long time, so then can exert very little force on the egg to bring it to a stop, and that's how you keep from breaking it. You can also, if you want to, the egg comes to you, just go like that. You'll stop it. You'll break, but you'll stop it because you've used too small of a time, so you're going to have to use a large force, okay? And you'll break the egg. That principle can be applied, to many things, right? When you jump up, why do you bend your knees when you land? More time, less force. You won't hurt yourself, okay? Why can't a stuntman jump out of a, 10-story building and land on an airbag and walk away? More time, less force, okay? So that's a little bit of just concepts, but again, if we plug this in and factor out the mass as we're going to do if it's constant, we don't really have any increased problem-solving power from F net equals ma. So it's really, we would not introduce something if it didn't lend us some kind of way to solve problems that we didn't have before. So we now have to really establish when is it that momentum as a method starts to shine and be the way to go in attacking a problem. So let me show you that. So when is a momentum is a useful calculation tool when? So here is when it becomes useful. Here we have Newton's third law. When two objects exert forces on each other, they're equal and opposite. Well, momentum is what allows us to turn Newton's third law into a conservation, a new conservation. Okay? So let me show you. So let's say I have, here's my object 1, here's my object 2. They're exerting forces on each other. I guess it doesn't matter if they're attractive or repulsive. Their point is just that they're equal and opposite. And let's figure out what we do. Well, this is the force on object 1 from object 2. The force on object 1 will change its momentum. Over here, this is the force on 2. That will change 2's momentum. All right? Now, if I were to go down this road, of course I could replace this with this, and I would get the statement that we are very familiar with. We'd say m1a1 is equal to minus m2a2. I think you had a problem like that on your homework number 4 or 5. You had a parent and a child pushing off each other on the ice, and you found that even though they exerted equal and opposite forces on each other, the child had more acceleration because why? Less mass, right? Okay? So rather than just going down that road, let me go down another road. I'm going to cancel the times. Now you say, how can I get away with that? Well, the time that they experience their forces is the same because it's coming from each other, right? So 1 can't touch 2 for longer than 2 can touch 1, right? So the time that they're in contact and exerting forces on each other is a common time, right? You can't touch without being touched, right? So we have a common delta t is their interaction time. You can say if you want delta t1 equals delta t2, they're one and the same. So now let me go ahead and put in, if this is the delta P1, this is M1 V1 final minus M1 V1 initial, that's the delta. And over here, I have a minus sign, of course, in the front. And then I say the same thing for mass 2. If its momentum changes, that change will be M2 V2 final minus M1, sorry, what? M2 V2 initial. There we go. Now that may not look like much, but I'm going to pull the same trick that I did with my energy thing. I'm just going to put all the initial stuff on one side and all the final stuff on the other side and see what happens, and we're going to find a conservation. Here's what I get. I'll put all the initial stuff on one side. I'll put all the final stuff on the other side. And that's very nice that I get the same thing on both sides. I get that M1 V1 plus M2 V2 is conserved. They can exert forces on each other, but if they exert forces on each other, well, that means that the sum of these two is still going to have to be constant. Now, what is this? This is momentum of 1, this is the momentum of 2, and collectively that's the momentum of the system. So the momentum of the system is conserved. Okay? So if we define momentum like this, momentum is mass times velocity, we find that Newton's third law, if Newton's third law is true, it means that the momentum of the system is conserved. Okay? So here's what we have. If we think of momentum of object 1 as like a bank account. Now here it's a little bit weird because it's a vector quantity. So it's like getting money out and it's $5 to the left, or $5 20 degrees from such. Okay? So it's a account with a vector nature. We have another account for the momentum of object 2. They can exert forces on each other so I guess I'll call that F internal, because it's internal to my system. If they exert forces on each other, what that'll do is it'll take momentum from one and give it to the other, but the total will be conserved. Okay? So what we find is that internal forces in a system, all they will do is take momentum from one, give it to another, but the total will remain the same. Now I could even have a third object. Momentum of object 3. But maybe I don't like object 3. Okay? So then, if that exerted forces on these, I might call that an external force. If I included 3, if I included in my club, then I could say that the momentum of all three was conserved. But sometimes I don't like to invite everybody in, okay? Sometimes two is enough. So then, of course, if I didn't include this in my system, then the momentum of these two is not necessarily conserved because some of it's going over here, okay? So in your system, you define who's a member of your system. In any forces acted on within that system will just trade momentum amongst the members. But if there's anything that's external, then that will trade momentum, but it'll take it out of what you defined as your system. Okay? So this is my system. Any forces inside or internal, they don't change the momentum of the system. If you trade with anybody outside, then that's considered an external force, and that will change the momentum of the system. Okay? So what we find is that if the net external force on a system is 0, and by system, that's however you've defined it, then the momentum of the system is conserved. And part of the art of this, by the way, is defining who's going to be a member of your system and who's not, okay? So, let me give you an example of this. I'm going to have a table. It's going to be flat. It's going to be smooth. And I'm going to have two objects, A and B, heading towards each other. Let me give you some values. Let's say that the mass of A is 1 kg, mass of B is 2. Let me give you some initial speeds. 3 meters per second, 4 meters per second. So this is my initial state of the system. They're going to have some kind of collision, like so. And then, this is during, and then they bounce off. This is my final state. There's a number of different outcomes for how they bounce off. Maybe they both stop, maybe one stops only, maybe they both go in the same direction afterwards, maybe opposite. We'll find out how to calculate that. But for right now, I want to just tell you that A exits at a speed of 5 meters per second, and I want to know how fast does B exit. Okay, so let's talk about how we might approach this. Well, you definitely wouldn't want to pick A only to look at, because A clearly changes its momentum. It changes momentum. It's going at a different speed and different direction at the end. And the reason why A changes momentum is a very good one. It feels a net force. It feels a net force from the other guy, B, right? So it would be silly to pick just one object, because then if it interacts with anything, that's going to change momentum. So I wouldn't want to pick just B either, but I am going to pick A and B together. That's my system. Because then that collision force that they experience is going to be internal. It's going to trade momentum between them, but it is not going to change the total. Now, what about a third thing? Well, there is a third object. It's the table, but I'm not going to include it. And here's why. It's a flat table, so N and Fg cancel. And it's smooth, which means that I can neglect kinetic friction, which means that these two objects are really pretty isolated on their own. So I don't really have an external force on them. So what you want to do is you want to pick your system that is relatively isolated from the environment. The members of your system can interact with each other but have no appreciable interaction with anybody else. Then you can have hope that the momentum is going to be conserved. So let's count up the momentum. We do have to go back to vector land, so I'm going to have to pick a positive axis. Let me throw in the values. I have a 1 kilogram mass. Its velocity initially is +3. Notice I have to supply directional information myself. Momentum is a vector, so don't just plug in the speed. Consider the velocity. I have a 2 kilogram mass, and its velocity is -4. So I add these two up, 3 and -8, that's -5 kilogram meters per second. That's the momentum of the system. That's the initial momentum of the system. It's negative because I have more mass going faster to the left than I have mass to the right. That's why it overall came out negative. That momentum had better all be there at the end, okay? Because the internal force can only trade momentum, it can't change it. So on the other side, we have that mass A, 1 kilogram, has a velocity of +5, or sorry, -5. And then we have our 2 kilogram mass, and we want to know what its final velocity is, v final x, which you can, by inspection, already tell is what? What is this? 0. Because this already has all the momentum of the entire system in it itself. So in this particular case, we discovered in order for momentum to be conserved, V actually has to come to a dead stop. Because the momentum that is initially carried by both members of the system is all hogged by one of them at the end, the other one has to stop. Okay, so let's call it a day there, and we'll pick this up next time.